All right, lesson 7.3. Make sure we fill out the attendance, but I'm going to get started. The items we're going to need today, if you go to your digital classroom here and go to your daily, weekly links, I'm going to open up the formula chart. We're going to use that heavily today, but before I even click there, I'm going to open up my pre-programmed graphs. So I'll have that open and available for later on. But truly, for the bell ringer, what I'm going to be using is the formula chart. So now I'm going to go open up my formula chart and blow this up. And this might be a little bit different than you saw last class. I realized that there was a difference between the 2019, 2020 version and the 2020, 2021. And the 2021 is the, believe it or not, older version. The 2019 was an update, and this one is long story short, this is the better one. So I've changed it. It's going to be different than what you saw last time. A couple of these are flipped around, but you can tell the eccentricity better. And that's why I like this formula. Hopefully the district makes this a permanent switch back to use this one. Let me blow this up. We are going to look at number one, number two now. So number one says, write an equation in standard form for the ellipse with all this information. When you're working on conics, especially in pre-calculus, according to Texas, the TEKs are written that you should be able to write an equation given some key attributes. Those are my terminology. But write an equation, standard form, and we're looking at an ellipse. So what I'm going to do is go to the ellipse, and I'm going to draw off what's in common. And this is one of those changes. If you have a good memory, you'll realize this is different from last class. What's in common for an ellipse is that both formulas are going to start with some quantity being squared over a squared plus another quantity squared over b squared equals 1. So what I'm going to start off over here was with, I don't know what that first quantity is, but I do know it'll be placed over a squared, or in the numerator, and a squared in the denominator. And my second fraction, I don't know the numerator, but I do know the denominator will be b squared. All that will be set equal to 1. So that's what's common between the two formulas. And so I'm now going to start working with my information. When you see the word vertices, let's just do a little word association game. I want you to think of major axis, today there will be a new word, might not always be major, and we'll see that in a second. Or I want you to think 2a, that's the formula. So when I go to plot this, this is in the terms of x comma y. So we have x comma y. That means I do the x value first, then followed by the y value. So the vertices will be left 3, down 1. Left 3, down 1. And the other vertice is right 7, down 1. These are my two vertices. So like I said, I want you to associate with major axis, because major axis, what that means, it's a line that connects vertice to vertice. So that's your major axis. And I want you to think of the formula 2a, because from the center, it's a units left and a units right. So here's what I'm going to do. We're going to calculate 2a from here. This point is 3 to the left. This point is 7 to the right. Think in terms of distance. So it's a positive 3 left, a positive 7 right in distance terms. So how far apart are these 2 points? If it's 3 plus 7, 10 units apart. So 2a equals 10. That's our major axis. My question for the formula is I got to get to a squared. So I'm going to go step by step. What does 1a equal? If a equals 10, if 2a equals 10, what does 1a equal?
5.
5. And so for the formula, what does a squared equal? 25. So I'm going to replace this a squared with 25. And that also tells me another piece of information. Since this is the major, the vertices, and it's going left and right, this value here, the a, is going to go underneath the x, which means this goes underneath the y. The letters that are with them, if you notice, is minus h and minus k. So I'll put here minus h, minus k. I got that because the vertices are going left and right, horizontal. So it's the horizontal, it goes with the x. Now, since the a is 5, we can discover the center. The center is going to be 5 units from either one of these. So I'm going to start with the positive numbers. It's easier. From 7, what's 5 back? 2. So if I checked it 1, 2, 3, 4, 5, you'll see that's the center. 1, 2, 3, 4, 5. Yep, they match up. They're 5 on both sides. So the center is right 2, down 1. Close that parentheses. So when I put this parentheses, the values lie. So I'm not going to say x plus 2. When I put in parentheses, it's going to lie. It needs to be x minus 2 because the h itself is 2. That's the center follows the formula h comma k. So the center is going to be 2 for the x minus 2. And then the value in the y parenthesis is going to be y plus 1 because, again, inside lies. It's technically y minus negative 1. Net minus a negative 1 is a positive 1. Which leaves us only one thing left to do. Solve for b squared. Let's continue on our problem. So we found all that information, 3/4 of the answer based off vertices. Now it says foci. Foci, if you remember, are the reflection points. I want you to associate in your brain that foci is going to give you your 2C. So these points are left 2, down 1, left 2, down 1. There's a foci. And right 6, down 1. There's my other foci. So this length is 2C. If I count them, this is 2 to the left. This is 6 to the right. What is 2 plus 6? So 2C equals 8. What does 1C equal? C equals 4. And I know the problem does not ask for C, but on an ellipse, there is a relationship between the A, B, and C, and it follows this, that C squared equals A squared minus B squared. So we can say C squared equals A squared minus B squared, where we know C is 4, which implies that C squared is 16. So 16 will equal, and we know A squared is 25. 25 minus our B squared. Now, you might already know the answer is going to be 9 here, but if you did not, you would subtract 25. And we would discover that 16 minus 25 is a negative 9. Negative 9 equals negative B squared. If you're trying to isolate B squared, you would then divide by negative 1. And we divide by negative 1, we get that positive 9 equals B squared. And so that would be our value right there, 9. So that would be the ellipse. If you wanted to finish graphing it, with that's telling you that if B squared is 9, that B is 3. That means from the center, this ellipse would go up 3 units, and it would go down 3 units. 1, 2, 3, and that's what this. When I connect all my points here, I would get what this ellipse actually looks like. I'll use this one. The ellipse would look like that. That's what it would look like. But you don't have to have that on this problem. All right, and I didn't put on there the minor axis, but the minor axis is this distance across here. That would be the value 2b. All right, number 2, it says, again, write an equation. And so we will go to the formula chart and figure out the basic parts of the formula, but we need to get the ellipse. So when I go to ellipse, I'm going to copy off what I think is in common, what I see is in common between the two formulas, both vertical and horizontal. And just like last problem, it's a parenthesis being squared, or quantity squared, you could call it, over a squared, plus another quantity being squared, divided by b squared equals 1. Quantity is another way in math of just saying parentheses squared. Quantity squared, parentheses squared, equivalent to one another. All right, our co-vertices. Before I do anything, co-vertices, mental association. When you see co-vertices, I want you to think minor axis or 2b. So these co-vertices will give me the length of the minor axis. So I go to plot them. It says left 6, up 3, 1, 2, 3. That's a co-vertice. Right 2, up 3. That's a co-vertice. Now this gives me, again, some information. This point is 6 units to the left. This one's 2 units to the right. How far apart are these 2 points? If this one's 6 left and this one's 2 to the right?
8.
8. So if 2b equals 8, what does 1b equal? B equals 4. And b squared equals 16. Good, Mariana. I do hear you quietly, but I hear you. Okay, so when I go to plug this in, b squared is 16, so I can place that in the formula now. And the thing that goes with it, this is where kind of what students forget, is whoops, because this is moving left and right, these 2 points, they're left and right of one another, that means the x parenthesis is in the numerator with the 16 in the denominator, implying y has to be here. And so this will be y minus k, this will be your x minus h. If you look at the formula chart, that's the numerators. So I've established all that, and we can establish one more thing. If b equals 4, we could find the center. The center is 4 units from either one of these. So if you just count over 1, 2, 3, 4, you could check it and go 1, 2, 3, 4. Yep, it's 4 either way. So that means the center is left 2, up 3. So I'll go to plug this in. X, it says minus h. The h is a negative 2. So when it goes in the parentheses, is it going to actually say x minus 2? When it goes on the inside, it's inside lie. So it's actually going to say x plus 2, because technically you have x minus a negative 2. So x plus 2. And then I have a 3 here. So 3 substitutes in for k. And so when I erase that k and replace it with a 3, you notice it looks like y minus 3, the lie of a positive 3. We're 3/4 of the way done, all off of co-vertices. What's left? The a squared. Our problem, we find out the eccentricity is 3/5. That there is a formula for eccentricity here on the formula chart. The eccentricity is c divided by a for all shapes. So if eccentricity is c divided by a, I could substitute and say 3/5 equals c divided by a. That means my c is 3, my a is 5. For our problem, we only need a. So if a is 5, a squared would be 25. And so I've now plugged this in right here. Now I will tell you that sometimes it doesn't work quite as simple as this, because this could be a reduced fraction, meaning the numbers could be like, say, 6 and 10, something like that. But they'd have to follow that Pythagorean type of relationship, which our formula says, let me find that c squared equals a squared minus b squared. C squared equals a squared minus b squared. If you plug in your numbers and checked, you would see it does work out that these aren't reduced, these are the actual values. You could say, okay, we know that whatever this relationship is, I'm gonna just test it. Does 9 equal 25? 9 is c squared, by the way, 3 times 3. Does 9 equal 25 minus 16? And yes, it does. So this does work out for us. Sometimes though they might be reduced. So for example, if b would have been an 8, these would also need to have been doubled. So just be aware of that. But that's our bell ringer. With that, let's transition lesson 7.3. This is for hyperbolas. I do say I have some graphs I think are very helpful if you want those. But today I'm going to focus on a lot of algebra. All right, we're dealing with hyperbolas. So what's different with a hyperbola from an ellipse? Well, let me just kind of do a quick diagram and I'll show you what's a little different on these. So on a hyperbola, or let me start with an ellipse. Let's say we have an ellipse. I'm going to try to make an ellipse the best I can. So there's one portion of the ellipse. There's the other portion of the ellipse. Let's just say this ellipse looks like this. And every ellipse we learned last class has 2 foci. They would be on the major axis. So these are my 2 foci, foci 1 and foci 2. There they are. Or you could say 2 focuses if you want to use improper English. Well, what's different on a hyperbola is basically this portion of the graph gets shifted down here. This portion of the graph gets shifted up there. And that's basically how our picture is going to look. That will be our hyperbola. You'll still have two focuses or two foci. They're always located on the inside of the shape. They're still the reflection points, but this is going to be the look of our shape. The word transverse axis is from vertice to vertice. So the vertices are still in the same location where they were on the ellipse. They're at the points of these. These would be my vertices right here and here. And so instead of calling this a major axis, whoops, press the wrong button there. Instead of calling this a major axis, they're going to call this a transverse axis. And we will find out later the reason is because on a hyperbola, that might not actually be the greater distance. It might be a shorter distance than the conjugate axis. But let me see if I can click the right button this time. Let me just use this one. That right there would be called the transverse axis. I don't like that color. Let me try this one. There we go. That's the transverse axis right there in green. That's the transverse axis. The conjugate axis has to do with the width. And I'm going to show you that on an actual problem. So conjugate transverse axis, I want you to associate in your brain. It's much like the major axis. So I'll do this similar to, approximately. It's not the same thing, but it's approximately. What I do need you to know is that's equal to 2a. Whereas the conjugate axis is going to be equal to 2b. It's kind of like your minor axis, if you will. So that's really the differences by formula. The difference is a hyperbola and an ellipse by formula, standard form, is that an ellipse has a plus in between and hyperbola has a minus in between the two fractions. So that's kind of the difference. So let's take a look, and we're going to first start with, and here's the textbook's method for graphing this. They have an error in the textbook. They needed to have a minus there. They did not include it. But that's what the textbook shows you about these two shapes. Notice this would be the transverse axis going across from vertice to vertice. On this one, this would be a vertical transverse axis, vertice to vertice. Conjugate axis is going to talk about the width. So we'll look at that as we go. So first, it says graph this hyperbola given this information. Well, just like ellipses and just like parabolas, the values with the x and y will tell you the shifts. Since there's no number up with the x in here, this has no shift, either left and right, and no shift vertically either. So this one is going to be located at the origin. That's the center of this hyperbola. So the shifts would come in the numerator with the x and y, but there's no number there, so there's no shift. It's at the origin. The next thing, this is just, again, like ellipse, is that the great value that appears to be greater is your a squared. Now, here's what's tricky, is when you look at 49 compared to 81, you'd say, well, 81 is the larger number. But you kind of think of this fraction being a negative fraction. So what would you rather have in terms of money? Would you rather have $49 in your wallet, or would you rather be in a spot where you owe your friend $81? Which one's better? To have the 49. So the positive fraction is always going to generate the a squared. The negative fraction is going to be the b squared. Okay, so from here, it's going to be very similar to ellipses. So a squared is going to be 49, which implies that if we take the square root, what is the square root of 49? 7. We should go from the center, it's with the x, horizontally left 7 and right 7. So I'll go 1, 2, 3, 4, 5, 6, 7. There's a vertice. And then 1, 2, 3, 4, 5, 6, 7 to the left. There's a vertice. Now I'll walk you through what's different from a hyperbola to an ellipse. Well, on a hyperbola, we say that's 81. And b would equal the square root of 81, which is 9. What's different is this. Don't draw what I'm about to draw in purple. I'm about to do an ellipse. In an ellipse, you would go up, down, and down 9 from the center. And then we would connect those 4 points. We'd say, okay, here's my ellipse. My ellipse will look like that. But that's an ellipse. What's different with the hyperbola is this. You don't plot those 2 points from the center. You go up and down 9 from the vertices. So I'm going to go from the vertice up 9. This is we can call it the co-vertice. Down 9. co-vertice. Now I'm going to come to this side and do the same thing. Up 9 from this vertice. Sorry, let me be more specific. Up 9, and from this vertice, down 9. Here are co-vertices. Notice that there's 4 of them now instead of just 2. And hyperbolas have a little extra information called a asymptote to help you draw or to help you with the width. There's these asymptotes that go through diagonally through the co-vertices, through passing through the center and another co-vertice like that. So let me straighten this one out right there. There we go. And I'm about to give you the equation for how you find that. But the hyperbola itself will originate from the vertex, just kind of like a parabola now. So you'll see that hyperbolas are kind of a combo of parabolas and ellipses. But like a parabola, it originates from the vertex, not from the center. It originates from the vertex. But what it's going to do is it's going to curve around and follow these asymptotes. Like that on this side. And over here, it curves around like this and follows that end. Same over here. It comes out and curves out and curves. There is your hyperbola. So we graphed it like the instructions asked. Now I'm going to add one piece of information here because it doesn't come up as much in the lesson, but it's very important for solving problems. It's very helpful information is how do you get the slope of these asymptotes? You can see on their picture, they say it's 9/7 and -9/7. Well, the formula chart tells you, and I think it's helpful to see the formula chart. This one was this standard form is the horizontal, which has the x value being positive. So it's this set of equations here. Notice that it says for the asymptote, it still uses a y minus k. It doesn't square the parentheses, but it uses y minus k. It uses x minus h. But right here, for the slope of the line, this is in point slope form. These are a point. This is the slope. In point slope form, it takes the slope as being b divided by a. Where does the b come from? What b comes from, it's the square root of the rise quantity here. The rise deals with y, divided by the square root here coming from the run. So it's rise over run. You remember that term from Algebra 1? You bet. Rise over run. So they got the equations 9/7. How did they get that? They took the rise, which is the y, the b was 9, and they divided it by the run, 7. So it's positive 9/7 and negative 9/7 because you have two of them, a positive and a negative. So that's how you get that ratio. It's just for this equation, I'm going to write it as y minus k equals rise divided by run. And I should do a plus and minus because you'll always have a positive negative one of these times x minus your h. Whatever their h may be on any given problem. So I showed you one. Let me show you a second. It says graph this hyperbola. So let's just start with where the center will be located. All right. I have y plus 4 inside lie. So which way is that actually going to shift my graph? Up, down, left, or right 4 units? So with y. So it's either going to be up or down. Down 4. So we're going to go down 4. And the x, it has -2. So is that going to be left or right 2? Right 2. So the center of this graph is going to be down 4, right 2. So down 4, right 2. There's the center of this graph. Now, for the rise and run and all that, you go off of these terms. So remember, the positive fraction is for hyperbolas is always the a squared. The b squared is going to come from what I call the negative fraction. So a squared equals 4. What does that mean a actually equals? 2. Now this component is with the y, which means it's what I would call the vertical component. I'm going to go up 2 units and down 2 units. Up 2 units, vertice, down 2 units, vertice. A's give you vertices. A's give you the major axis on an ellipse and a transverse axis on a hyperbola, just for the record. So there's our vertices. The transverse axis would be this length of 4, would be 2 times the A. Okay, now on an ellipse, we would go left and right 3 units from the center. And I'm getting 3 because the square root of 9 is 3. For an ellipse, you'd go from the center left and right 3. What's different on a hyperbola is you go from your vertices 1, 2, 3. That's a co-vertice. 1, 2, 3. Co-vertice. 1, 2, 3. Co-vertice. 1, 2, 3. Co-vertice. I'll add in my asymptotes. So your asymptotes are diagonal lines passing through co-vertices like that. And this one this way, across. And then to draw your hyperbola, you originate it from the vertex or from each vertice, and you just follow your asymptotes. Like that. And the same thing on the other vertex. Like that. This, notice, is a vertical hyperbola. These asymptotes would follow this equation. It's always going to be the y minus k. So let me write it up here, asymptotes. It'll be the y minus k, which in this case is y plus 4, equals plus or minus the rise over run. So let's think, which one's the rise quantity? Is it the y quantity or the x quantity? Which one would be rise? The y. So it'll be 2 over the run quantity, which is 3, times x minus 2. There's your equation in point slope form. And you can see they did not leave it in point slope form. They distribute the 2/3 and then subtracted the 4 over. That's what they did over here to get this equation. If it were up to you and you just had to write an equation, I would use point slope because it's a whole lot easier. In Algebra 1, most teachers teach you a lot of slope intercept form, y equals mx plus b, because the equation seems so simple and it's easier for students to latch on to something. However, the more complex you get in math, using point slope is very helpful because you don't have to do as many calculations later on. So that's, if you're wondering, why do you have 2 forms? This is really more powerful for you as you get older. So you don't have to keep doing calculations. This right here is slope intercept, and you can see how unpretty it is over here. With that, I'm going to give you your first DOL. I want you to graph this equation. What I recommend, I added a point for co-vertex. If you're on your own and you just plot on your piece of paper the center and then do the rise and run quantities, you ought to be able to come up with one of these 2 points. Notice that the point is different on all 4 graphs, because I totally understand that these graphs, it's hard to see what's different, what's alike. They're so zoomed out, it's very difficult. So what I would recommend you do is try to find your co-vertices. So do the steps required to find a co-vertice. Find your center, find your vertices, then your co-vertices. If you do that, that top right-hand co-vertice will be how you can determine your solution here. DOL number 1. All right, so now let's take a look at doing some more general form conversions to standard form. So it says graph a hyperbola given by this equation. Now what we could do is go to the calculator and graph it that way. But I'm going to show you first, I told you algebra today, of how to do so, of how do I transform this to standard form, and then how do I graph that. So with conic sections, we do a lot of completing the square. There was a pre-step I've recommended. I've told you in the previous days, I wanted to leave the steps the same. So I called it a pre-step. And so I'll write that here. The pre-step here, when you're writing an equation for a hyperbola or an ellipse for that matter, is that you need to get the constant by itself. Notice that's what's in common with these for both ellipse and hyperbolas, is that the constant is by itself. Whereas a parabola, you get the x and y separate. So that's what I'm going to do first here, is I'm going to get the constant by itself. The constant's 28, so I'm going to subtract the 28 to isolate it. And also with the pre-step, I am going to gather my x's together as a grouping and my y's together as a grouping. So I'm going to, and I need a little space because we'll end up adding blanks. So I'll have my 4x squared, and then I'm going to put my 24x next to it. because this is going to be its own grouping. And then I will have a grouping for the y's. So I have a negative y squared plus 4y. And then I want to have another blank, because we'll have to complete the square there, equals a negative 28. And since I added 2 blanks on the left, just to be consistent, I will add 2 blanks on the right. 1, 2. That's my pre-step. From there, we go into our 4 steps. You might remember from last class, I said divide A. Really, the better terminology here is to do the GCF. GCF your A from each grouping. I'm going to change GCF, greatest common factor, A from groupings. So I'm writing that because I think the math terminology needs to be better, from groupings. So I'm going to greatest common factor the A out from each grouping. So on the first grouping, I'm going to greatest common factor that 4 out, which means when I divide out the 4 over here, I need to divide this B by 4 as well. And when I do this side over here, I don't have a, my coefficient just looks like a negative. It's actually -1. So I'm going to divide this one by -1. So this was how I wrote it last class, divide A. Now I'm going to just call it GCF A out from groupings. So I have 4 times x squared plus 6x plus a blank minus 1 times y. And let's see here. I have a positive 4 divided by a -1. That's going to become a -4 plus a blank equals, oops, I almost forgot the negative right there. Negative 28 plus a blank and another blank. That's step 1. Step 2 is we're going to divide our B by 2. So I'm going to take my B value right here. I'll have 2 B values, each grouping, and I'm going to divide that by 2. So, oops, I put a -6. It's a +6. +6 divided by 2 is a +3. On this side, I have now a -4. So -4 divided by 2 equals -2. That's step 2. We do that for both groupings. Again, just like an ellipse. Step 3. We are going to square that B divided by 2 value. So B divided by 2, but that value is going to be squared. So I'm going to take out my B divided by 2 here, and I'm square it. What is 3 times 3? 9. And over here, I take my B divided by 2, and I square it. What is a -2 times a -2? +4. Now, I would love to tell you, all you have to do is put a 9 and a 4 there, but that's not exactly accurate because this 9 is actually getting multiplied by 4. So it needs to be a 4 times 9. And over here, I have a 4 times a -1. So I'll put the -1 in parentheses, otherwise it'll look weird, plus minus. -1 times 4. Now we get to step 4, the simplification. And this is the fun part because this is where our answer comes from, or an equation comes from anyways. So I will have 4 times all of this quadratic grouping right here. But we learn, I'll show you by proof here, that the reason you do complete the square is that trinomial is called a perfect, it'll be factored as a perfect square. Meaning, when I take the factors of 9 that add up to 6, what 2 values do we get? What are 2 factors of 9 that add up to be 6? Would it be 1 and 9 or 3 and 3? 3 and 3. And if you remember from the very first lesson of the school year, is when you're factoring a trinomial, not after you find these 2 factors, you split this a power. And so it'd be an x, and it'd be x plus 3 and another x plus 3. I have x plus 3 twice, which means x plus 3 squared. What was the shortcut? Whenever you do this, completing the square, it's always going to be the variable and this number there, x plus 3 quantity squared. So over here, you could, if you wanted to, just go ahead and skip to it and say it's going to be a y. Oh, I didn't forget. Let's put that square on there. That needs to be a squared. You can say the variable is a y. My value right there is a -2, so it's going to be y minus 2 quantity squared. But by proof, if you wanted to see it, what are factors of 4 that add up to be -4? The values would certainly be -2 times a -2. And so that's why we'd have y minus 2 and then another y minus 2. Since you have 2 of them, that's squared. And let's now see what this is equal to. This would equal to, told you we're going to use Desmos. Let me open up just a blank Desmos here. A -28 plus a 4 times 9 plus a -1 times 4, which I'm getting 4. So the value equals 4 here. Now, if this was the circle, this would be the final equation right there if it were a circle. Now, what would a circle look like? Let me go to the formula chart. A circle would just have the quantity squared with no coefficient plus another quantity squared with no coefficient equals some radius squared. Here, I do have a coefficient. So if you have a coefficient, this is for ellipses and circles, you divide by this number, they set it equal to 1. So I'm going to divide by 4, divide by 4, divide by 4, and this will give us our equation. The equation will be x plus 3 quantity squared over 4 divided by 4 is 1. These values just cross each other out, simplify. So you don't even have to put it over 1 because dividing by 1 doesn't change anything. So you can just leave it like that. Minus, I don't need this 1 there either, y minus 2 divided by 4 equals 1. So we have a lot of things can't simplify out of there in this problem. There's our equation. So if this is our equation, let's now graph this. So I'm going to copy it, and here we will graph this now to see what the graph looks like. So we need to shift. It's inside the lie, so I'm not going to go on the x-axis to +3. I'm actually going to go left 3. So we go left 3 units. And this one, again, it lies. So on the y-axis, I'm actually going to go up 2. So left 3, up 2. There's my center. Now remember, there's no denominator here. So it's the same thing as if we had set it being divided by 1, which means our a squared, because this is the positive fraction, is 1. A is 1. So it's underneath the x. So I need to go left and right 1 unit for my vertices. So left 1, there's the vertice. Right 1, there's a vertice. Again, you don't have to have that denominator, but you could set it as being over 1. And then my b squared is 4. So b equals 2. From, or when you graph these, you go from the vertices. I would go up 2, down 2, up 2, down 2. These are the co-vertices. When you graph a hyperbola, those will represent your asymptotes. As I kind of mentioned before, that is the rise value over the run, which in this case would be b divided by a, since b is with the rise quantity of y, a is with the run quantity of x. So there's my rise over run. Your hyperbola itself would originate from the vertices and follow this way and this way. And over here from the vertice, it'll follow that asymptote, and this side of the hyperbola will follow that into the asymptote. And so there's your equation. If you needed to write the asymptote, it's just because this is so important for asymptotes to know this. I'll put it in there. It's y minus k, so it'd be y minus 2 equals plus or minus the rise quantity, which is 2, over the run, which is 1. 2 over 1 is simply 2 times the x minus h, x plus 3. Those would be the equations for your asymptotes. I mentioned I was going to show you from a graph. How would you get your solution if you were doing this from graph? Okay, let's just say we were going to do this from the graph or from Desmos. If you want to get your equation from Desmos, what would you do? Well, you would start with, if you're going to write an equation, you'll have a parenthesis squared over a squared minus another parenthesis squared over b squared equals 1. Okay, so how could you get all this from a calculator? If you go to my calculator number 18, and this is really the extent of what I'm going to be doing on calculator today. Let me just close this one. If you go to calculator number 18 and click on Desmos, I said that and I just realized I'm a liar. Later on, we will use calculator for an example. If I open up calculator 18, I'm going to plug these values into the sliders here. So A is referring to your x squared, which I have 4x squared, so I'm going to make a be 4. My b is referring to the variables x times y, which I don't have any of those. I'll leave that as 0. C is the y squareds. I have -1 of those. D is the x quantity, which is 24. E is my y quantity. Let me scoot this over just a slight bit so you can see. E is my my y quantity, which I have 4 of those. And F is my constant, which is positive 28. Now, notice all of this is, in my calculator is programmed as if it's on the left side of the equation. If you have something on the right, on a different problem, you would need to subtract it or add it over so that everything's on the left side of the equation. It's set equal to 0. So here's my hyperbola, just like we had a second ago. If you click on key attributes, you could plug in your values. So now let me shrink this so we can see them all. The way you would solve this is say, oh, well, here's what I know. A is 1. So 1 squared equals 1. Anytime you divide by 1, you don't need that denominator, so that would go away. B squared is 2. Well, 2 squared is 4. So if that's 4, I'll just put a 4 here. When you look at the picture allows you to see that it's horizontal, which means the A goes horizontally with X, the B would go vertically with the Y. So I need to have Y minus K in this parenthesis because that's the B, and A is vertical, so X minus H. I don't know why I put a 4 there. I meant to put a K. Let me erase this. Minus K. There we go. So now I'm back on, and so I plug in these numbers. H is a -3. I make it be a lie, so it actually goes into the equation as a +3. So this becomes a +3. The K is a 2, so when it goes into the formula, it'll go in as a -2 because the inside's a liar. And just like that, we get the same equation. Oops, same equation we had right here. So that's how you could use a calculator for this. I do have other values as well. This will tell you your transverse axis, because it's a hyperbola, conjugate axis, and the slopes, plus and minus 2 for my asymptotes, which is just what I had there, plus and minus 2. So all that is on that calculator. So you can use whichever technique you like. Do a graph, example 2. If you're going to use my calculator, make sure you cannot have this equal to -119. If you're going to use my calculator over here, you need to set your value as being equal to 0. So I'll give you that as a FYI. Make sure you set this equal to 0 if you're going to use my calculator to solve this. But all these pieces of information should be on my calculator. DOL number 2. Example 3. Let's write an equation for hyperbolas. Okay, so for this unit, anytime you write an equation, what I would highly recommend of you is to go to the formula chart and find out the equation for the shape you're looking at. So in this case, we are looking for a hyperbola. So I'm going to go to the standard form of a hyperbola and copy down what's consistent between the two. And it is very, very similar to what we said was consistent to an ellipse at the start of class. What you're going to have is a quantity squared divided by a squared. And the one difference between this and the ellipse is you'll have a minus another quantity squared over b squared equals 1. Now, this tells us foci. And before I even plot this point, I'm going to ask the class, Foci. What's the formula that represents foci? Now, I'm going to give you a hint here. Vertices is like transverse axis or major axis, which was 2A. Co-vertices is like minor axis or conjugate axis, 2B. Foci is the one left over,
2C.
2C. 2C is the foci. So when we plot this, we'll get our foci. So I go 1 to the right, 5 down. There's a foci or a focus. Since it's only one of them, there's a focus. And I go 1, 1. Here's the second focus. So there's my 2 foci. So by distance, that's 1 up. This is 5 down. That means they're 6 apart. 2C equals 6. Well, 2C equals 6. What does 1C equal? 3. Good. So the center of our hyperbola will be 3 units away from either foci. 1, 2, 3. 1, 2, 3. So there's the center. Now, before I plug this in, because we don't know yet where to plug in the center like X and Y, you need to realize that the foci are telling you that it's a vertical because they're stacked vertically. This is vertical, which means it's going to be Y minus K on this parenthesis and X minus H in the second parenthesis. Now I can plug in the center. The center is right 1, down 2. So to go right 1, it's going to be lie. So is it going to be up X plus 1 or X minus 1? X minus 1. And then what about to go down 2? Will it be Y minus 2 or Y plus 2? Y plus 2, because it's going to be technically Y minus a negative 2. Turns it positive. Okay, and we know C is 3, but can't do anything else. So I'm halfway through. Now it tells me transverse axis. Key vocabulary. Transverse axis is just like your major, but for hyperbola. Transverse comes with the letters or formula 2A. So 2A equals 4. If 2A equals 4, what does 1A equal? Okay, if A equals 2, what does A squared equal? 4. So I can now plug that in. A squared is 4. So we're left with the B squared. Well, on the formula chart, we're told for hyperbolas, there's a relationship between the A, the B's, and the C's. It is that C squared equals A squared plus B squared. It is the Pythagorean theorem. C squared equals A squared plus B squared. So we know C is 3. That means C squared would equal 3 times 3, which happens to be 9. So I can substitute in 9 here. 9 equals 4 plus B squared. If you don't know it's 5, you could find that out by subtracting 4 to isolate the B squared. We get that 5 is B squared, and since 5 is B squared, you can plug that in and you have your answer here. That's my equation. By the way, if you wanted to graph the transverse axis, what that was saying is it's 4 units long and it goes through the center towards the foci. So it'd be like that. From there to there, that's 4 units. That would be your transverse axis. There would be a vertice. There would be a vertice. That's what that gives you, graphically speaking. All right, part B. It says write an equation. So again, whenever you write an equation, I would recommend go and copy from the formula chart the standard form for this shape, which hyperbola. But what's common is that you have a parenthesis squared over A squared minus another parenthesis squared or quantity squared over B squared, and you would set that equal to 1. So it looks like they gave us vertices. All right, you tell me, mental association. When you hear vertices, what should you think of? A, yeah, it's like your transverse axis, kind of like the major axis from ellipse, and that's going to equal 2a. So let's plot these points. It says go left 3, up 10. Go left 3, down 2. So there are my two vertices. Let's determine what we can from here. And if you think in terms of distance, this is up 10. This one's down 2. For distance, you're positive 2, positive 10. How far apart are those? 12. So 2a equals 12. What does 1a equal? 1a has to equal 6. And for the formula, that means a squared equals 36. Because these are stacked vertically, we can state that y minus k is the numerator of the positive fraction, and x minus h is the numerator of the negative fraction. I should say x minus h squared and y minus k squared are the numerators. Now let's see if we can find the center. If a is 6, we can. That means 6 units away from either point is the center. And so this one's up 10. I'm just going to go subtract 6. It takes me to 4. That should mean my center there. It should be left 3, up positive 4. So when I put these in, it's going to be a liar. So the y value of 4 is going to look like a negative 4, y minus 4. And the negative 3 value is going to look like x plus 3 because they lie. X plus 3. So the transverse axis, by the way, has a length of 6 units. Now it says conjugate axis. All right, word association. Conjugate axis. What should you think of when you hear conjugate axis? 2b. It says 2b equals 6. If 2b equals 6, that means 1b equals 3. And if 1b equals 3, then b squared would equal 9. So 9 would go into the problem right there. And this would be our equation. So the conjugate axis, I don't have it graphed here. That would be left and right 6 units from the vertex or vertices. So it would be left and right 6 units from the vertices like this. That's what that would graphically look like, where you'd have co-vertices at either point at the ends of these. You have co-vertices. All right. Let's take a look now at DOL number 3. I would like you to write an equation for a hyperbola given these foci and this conjugate axis. Please, please, please just try to graph this on your own. If you just plot the graph and use the vocabulary listed here, you want to be able to solve the problem pretty quickly. Let's take a look now at DOL number 3. Let's take a look at example 4. It says determine the eccentricity of that equation there. So eccentricity is a formula we've seen. It's the same no matter if you're what conic section you're looking at. The eccentricity formula is c divided by a. So I'll put that down here, that the eccentricity is equal to c divided by a. So on our problem, hyperbola, that's anytime you have a fraction squared minus another fraction squared equals 1. Your hyperbola, the a squared is always the positive fractions denominator. So a squared equals 32. The b squared is the negative fractions denominator. B squared equals 25. We need c divided by a, which means that we could find a really quickly. It's going to be the square root of 32, but we're going to need the value c. So we're actually going to need a second formula for this problem, and that is the ABC relationship. And that says that c squared equals a squared plus b squared. C squared equals a squared plus b squared, just like the Pythagorean theorem. So there it is. So what does that mean for us on this problem? Well, I could find my c squared by saying c squared is going to equal 32 plus 25. 32 plus 25 is 57. So c squared equals 57. then C would equal the square root of 57. Now I'm going to try to simplify this real quick. Let's see if we can do so. I'll use upside down division. 2 does not go in 57, the prime number 2. I'm just going through prime numbers here. 3 does. 3 goes into 5 one time with the remainder of 2. 3 goes into 27 9 times. Now here's the problem with 19. 19 is prime. So the square root of 57 is equal to the square root of 3 times the square root of 19. Neither one of those can be reduced because I don't have 2 of those, and they're both prime. So C is the square root of 57. A, on the other hand, would be the square root of 32. But that can be reduced. Let's say A equals the square root of 32. If I did upside down division here, 32, the prime number 2 can go into 32 16 times. And I could do a shortcut here and say that's going to be 4 and 4. But I'll continue on using prime numbers. 2 goes into 16 8 times. 2 goes into 8 4 times. 2 goes into 4 twice. Now it's all prime numbers. Pairs come outside. I mean, technically it's the square root of 2 times 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 square root of 2. But practically, how will it simplify? Our pairs come outside the square roots. It'll be 2 times 2 times the square root of 2. 4 square root of 2. That is what A will equal right there. So A is 4 divided by square root of 2, which if you want to leave this if you want to rationalize the denominator, you need to shoot that square root up and then we'll multiply. And so it'd be the square root of 57 times the square root of 2 all over 4 times 2, which is 8. And so one more little simplification, we'll have it rationalized. It's the square root of 104 divided by 8. That's our eccentricity. But do you need to do all that? Oftentimes, no. Oftentimes, all you have to have is the decimal value. So we could have gone all the way back to the start and just typed in from the get-go into a calculator. Let me just get a blank one here, or I'll just press enter here. From the get-go, we had that C was the square root of 57. And so we could have said square root of 57 divided by, we knew A was going to be the square root of 32. Square root 32, and we could have gotten the decimal form of the answer right away. Let's check real quick to make sure our answer was right. Square root of 104. Oh, I wrote 104. I needed to put 114. It's going to be 114. See, that does not work. It needs to be 114. I just realized I did bad math. 2 times 57 is not 104. It is 114. That was terrible math. Let's see here. 114. And there's the rationalize. If you're doing Alex, you need it in that form. But for most of the stuff we'll see in this class, you can use the decimal form. All right. With that, I'm going to give you one where you only have to give me the decimal form. Determine the eccentricity of that equation shown there. DOL number 4. All right, example 5. There's this thing called a discriminant, and it's just given a general form, you could determine what shape the equation would be without completing the square and without using technology by using this formula here. It's all about what b squared minus 4ac would equal. If it's a negative number, it's either a circle or ellipse. If it's a equal to 0, it's a parabola, and if b squared minus 4ac is positive, it's a hyperbola. How do you know if it's a circle or ellipse? If b is 0, and A and C are matching values, it's a circle. But if B does not equal 0 or A does not equal C, then it's going to be an ellipse. So that's all it's saying. What many students do is they just graph this. If you type that straight up into Desmos, it'll show you the shape, which you could do. I'm pretty confident you could just type that into Desmos and see the shape, but I will walk you through the algebra here. You would say b squared, here's the formula, b squared minus 4ac. That's what we're looking at. And so I will label, this is my b right here, the number of x, y's. A is the number of x squareds. C is the number of y squareds. So the algebra here would be 5 squared minus 4 times 2 times 1. So 5 squared is 25 minus 4 times 2 times 1 is 8. That is 17. 17 is greater than 0. If your value is greater than 0, it's a hyperbola. And again, that came from this set of information right here. Let me take that, cut it, and I'll paste it right here so you can see. But like I said, most students would just graph that, and that's totally fine. But you can see if the value is greater than 0, it's a hyperbola. All right, let's try the next one. Again, you can graph this, but I'll just go through the algebra. I'm going to say b squared minus 4ac. On this problem, I have 4 a's. That's how many x squareds. I have 4 c's. That's how many y squareds. And b equals 0. Because there's no, in this formula, there is no xy term. There's not an xy term out there, so b equals 0. All right, so I would plug in my numbers. 0 squared minus 4 times another 4, which is going to be simply 0, and 4 times 4 is 16, times another 4 is 64. So we're looking at negative 64. That's obviously less than 0, which means it's either an ellipse or a circle, and it all depends now on these two items. It says b equals 0. We have b equals 0, and a and c equal one another. So that means this is a circle. Again, if you graph this, you would find out that the image is a circle. And finally, part C. Use a discriminant, and I will go ahead and just paste that little chart up here so we have that for later. Here's the chart. My B value is 4. My A is 2. My C is 2. So it would be B squared minus 4AC. 4 squared minus 4 times 2 times 2. 4 squared is 16. 4 times 2 is 8, times another 2 is 16. That equals 0. 0 equals 0, and so it's a parabola. So there's using operand. You can use the calculator if you so desire, but here's your DOL number 5. All right, now let's take a look at example 6. This is a real-world example of how we use hyperbolas. It says LORAN, which stands for Long Range Navigation, is a navigational system for ships relying on radio pulses that is not dependent on visibility conditions. Suppose LORAN stations E and F are located 350 miles apart along a straight shore with east due west, or E rather, due west of F. When the ship approaches the shore, it receives radio pulses from the stations and is able to determine that it is 80 miles farther from station F than it is from station E. Find the equation for the hyperbola of which the ship is located. All right, so there's a key note on this for hyperbola. So there's a piece of information that expects you to know, but we need to know here is the difference in time will be equal to 2a. So first, if we try to draw a diagram here, we have a shore and we're gonna have a ship out on it, but I'll just do the shore here. And E and F are 350 miles apart. So E here is 350 to due west, which means to the west. So E is over on this side, F is over here. Now there's one other thing I guess I should include here with hyperbolas is these stations would be located at the foci. So that's an important piece of information they expect you to know. Now I'm going to just say the center, just to make this easier, is here, and we'll call the center 0, 0, which means this foci is 350 divided by 2 to the right, which is 175. And this foci would be negative 175. to the left. Now, somewhere out here, we have a ship, and it says F is 80 miles farther than E from the ship. So I put E twice, or F twice. This needs to be an E. E is closer to the ship than F. So wherever my ship is, it's not in the center. So wherever my ship is, let's just say it's there, it's going to be a little bit closer to E than it is to F. So if you measured these the distances from here, let me get a dotted one, sorry. From here to here, there is going to be, this one is whatever this length is. I'll just refer to it as X. This length is going to be X plus 80. X plus 80. That's the difference in these two. Now this up here says the difference is always equal to 2a. So here's what I know, that 80 is going to equal 2a. Which means if I solve here by dividing by 2, I can find out that 40 equals my a. Now for our equation, some things I can figure out here, I know why I put F there is because these are both foci, is that this is going to be a horizontal hyperbola. So what does that mean if it's a horizontal hyperbola? When it comes to writing an equation, you're going to have some x quantity being squared divided by a squared, which we now know is 40 squared. And since I'm going to say the center is at 0, 0, I'm just going to put it as x squared minus the y squared value over b squared. And that would equal 1. So I now know what 80 is, or a is, it's 40. I could say that C, I know that's C for center, but my C distance is equal to 175. And this would also be 175 this way. So C, if I wanted to use the formula that, let me pull that up over here. C squared equals a squared plus b squared. If I wanted to use this formula, we could solve saying c squared equals a squared plus b squared. And we know c is 175. So 175 squared will equal the 40 squared plus our b squared. So I'll go to our calculator here and start figuring out what these values are. 175 squared, we're going to need that number, and 40 squared is 1600. And so what I'm going to do here is just say, I'll fill it in, 3625. 3625 will equal 1600 plus b squared. And we would do our algebra saying we need to subtract 1600 here. I subtract 1600. And I'm going to write this value now over here. So b squared would equal 3625 minus 1600. It's 29025. 29025. For writing an equation sake, all you'd have to do is b squared. And so 29025 would go there. And that would be my equation. We could simplify that 40 squared. Instead of just leaving it as 40 squared, I'll go ahead and put in a 1600 here. And so that's what my formula would look like for this. Now there's a part B. So I'm guessing I'm going to need this equation. I'm going to copy this. And now let's take a look at part B. It says, find the exact coordinates of the ship if it is 125 miles from the shore. Okay, so here's my equation. And I'm going to also pull my diagram that I have here. Whoops, just the diagram. I take this diagram. All right, copy this. All right, and what we just determined is that this ship is, I'm going to delete this one. I'm going to delete a couple pieces I don't need anymore. Now that I know the equation, we know that this ship is 125 miles from shore. So we'll just say that ship, we don't know the x value. So it's I'll put X, comma. We do know it's 125 miles from the shore, and the way I've got it drawn, that would be a Y value. So if I needed to solve this, what I could do is I could plug in that as a Y. And so we'll say that this will be a little complex algebra. You could use a calculator to solve a lot quicker than I will, but here we go. It's equal to x squared over 1600 minus 125 squared over 29025 will equal 1. And so basically what's going to happen, our calculator, I'm going to do that algebra before simplifying, is you would add over 125 squared divided by 29025. And I'll add it on this side as well, 125 squared over 29025. So I will add that on both sides. And so we'd have that x squared over 1600 would equal 1 plus 125 squared over 29025. Okay, and so final deal to get x squared by itself is I would need to multiply by 1600. And so I'll multiply that, and I'll also multiply all this by 1600. Now that will give me x squared, and then we'll take the square root of that. So first let me go to the calculator and type this in. Let's see what we get. And I'm just going to clear off this one right here. I'll use that. So the value is going to be 1 plus 125 squared over 29025, there we go, times 1600. Now that's what x squared equals. And so we need to actually take the square root of all this number. So if I come over here, I highlight it, and I hit the square root. Whoa, that didn't work. Let me do Command Control Z. And this time I'm going to copy this. And what I'll do here is I'll do square root, and I will paste that. So the x would be, whenever you add a square root, remember we need to add a plus or minus. So here we go, x squared is going to equal 2461 point, let's just say 3264, and we would take the square root of this. But anytime in mathematics you add a square root that's not originally there, it needs to come with a plus or minus. But our problem, we know that the ship is closer to the east, which means closer to the left side. So I'm actually going to take the negative of it. I'm going to say x would equal the negative 49.61. I'm going to round to the nearest hundredth here. And so my coordinate for the ship would become negative 49.61, comma, 125. That would be the coordinate, and that's going off of miles there. I should do this miles here. That would be the coordinate if the center of these two stations is the origin. That would be the exact coordinate. So now you have one that you can work through and try to solve. DOL number 6. So let's take a look at the ACP type of problems here. So release questions that we've seen in the past for the ACP, it says a hyperbola has foci. Okay, I'm going to stop here. What is foci? What should you associate in your brain when you see foci?
2C.
2C. So 2C are found by these 2 points. So I'll plot a little graph up here. This says go left 4, up 7. So I'm just going to say a negative 4 there for the sake of time here, and put a 7 there. 7, there's a foci. And the other foci is left 4, down 11. So I went all the way down to 11. Here's my other foci. Now this tells me something. First, it's vertical, which means the y squared has to come first, which it looks like all the examples are that way. We could count, this is 7 units up, 11 units down. That's a total of 18 units. If 2C equals 18, we could solve for C. Say C equals 9. So now I can get the center. 7 minus 9 it would be down at -2. There's my center. So the center would be left 4, down 2. That's the center. And it looks like I can't eliminate anything there either. So all this information that they just gave us doesn't actually give us any, I can't eliminate anything from that, but I can from here. It says eccentricity equals 1.8. That means eccentricity, according to the formula chart, is C divided by A. So C divided by A is 1.8. Now, I'm going to type this into Desmos and show you something pretty cool about Desmos, is that let's just say you typed in 1.8 and you press this little fraction button, it'll tell you the fraction of that is 9/5. So this is saying that C divided by A equals 9/5. Well, we already knew C is 9, but now guess what we know? A equals 5. So now I know 5 squared has to go in the front, which eliminates B and D, because 5A squared would equal 25 since A is 5. And just write that A equals 5. So A squared equals 25. And now for the B, you could use your ABC relationship that says C squared equals A squared plus B squared. We know C is 9, so 9 squared will equal A squared. Why am I writing that way? 81 will equal 25 plus B squared. So I subtract my 25 over. I do this, I'm getting 56. 56 would equal B squared, which eliminates D. So the answer would be A. So I'm going to roll this over one more time and try again. It says a hyperbola has vertices at -14, -5, and 10, -5. Let's see here, -14. I'm just going to put it right there. Left 14. Left 14. There we go. Down 5. And this is a vertice. Oh, let me stop. What is vertice? What should we think of when we see vertice? Transverse axis, major axis, or 2A. So we go left 14. Doesn't look like much of a 14. Let's try that again. Left 14. We go right 10. Down 5. Okay, so these are my two vertices. I go 14 to the left, 10 to the right. That's a total of 24. 2A equals 24. What does A actually equal? 12. Good. Now here's what's tricky on this problem. It says the eccentricity is 11/6. So what's interesting is eccentricity we just saw is C divided by A. So C divided by A is 11/6, which makes us think that A is 6. But we know A is 12. What this means is this fraction has been reduced. So this fraction is equal to, if I got A to equal 12, what I could actually say is it's kind of like saying 2 times 6, which means the numerator it's 2 times 11. So my C actually equals 22. My A actually equals 12. Now it says, what is the value of B? I would use this formula to find B. So C squared is, I think, 444. Let's check that out. 22 squared is 484. Sorry, 484. So 484 will equal, A is 12. That's 144 when you square it, plus B squared. And finally, we would subtract the 144. 144. So 484, that's ugly math. 484 minus 144 equals 340. 340 equals B squared. And finally, to get rid of that squared, I would take the square root. Normally we say plus or minus, but B is always going to be a positive value. So B is the square root of 340. This says round to the nearest hundredth. So let's see what that is when I take the square root here. Square root 340, it'll be 18.44. 18.44 to the nearest hundredth. buzzer beater.
It is now the end of